All right, so now we're going to look at surface integrals of vector fields. This is different than surface integrals of scalar fields, though they're related. Okay, so the motivating example is this. So assume S is a surface that is submerged in a fluid. And here fluid is very generic. Just think about water for now, but it could be any typical fluid like a liquid or a gas, or it could mean things like electric fields. In fact, what we're going to be calculating is the flux of a vector field, which you've seen in physics. Okay, so anyways, we have S is submerged in a fluid. I'm just going to think about water, and it has a velocity field f of x, y, z. That's a velocity vector field f of x, y, z. Now we want to know how much fluid is flowing through the surface per second. So I'm just going to use, again, the example that I've been using, the upside down facing paraboloid, just because of all of the surfaces I can draw poorly. I think I can draw this the least poorly. And we're just going to look at this quarter here in the xy plane. And again, I'm going to think about giving this polar coordinates, or parameterizing this with polar coordinates. These are r curves because they have constant r, and then we'll look at curves. Let me find the blue pin like I was using before. And then these are the theta curves because these are constant theta. Okay, and now what I won't draw is the velocity vector field. So there's some velocity vector field that is defined on R3, and we want to know how much is flowing through this surface per second. Okay, so how much water is flowing through this surface per second? It's given by this sum right here. So delta VKJ represents the amount of fluid flowing through each patch per second. And so now we're going to use various approximations to see how we can approximate this, and then we'll take a limit to get so I'm going to draw
to
get an integral. This highlighted patch down here. So it'll look something like this. Okay, this will be a representative delta VKJ. And so how much fluid is flowing through this part per second? Well, I'm going to attempt to draw two vectors. The first is going to be the outward pointing unit normal. So this is the normal vector at that purple point. So in other words, there's like a 90-degree angle here, and then a 90-degree angle there. And the other vector that I'm going to draw is going to be f. This is f evaluated at r of SKTJ. So it's just the vector field evaluated at that purple point. Okay, so we're going to treat the red vector as being constant over this patch. That is, f is being constant over this patch. And the purple vector is being constant. That is, a normal vector is being constant over this patch. So then delta VKJ is going to be equal to the following. So f has a component that is parallel to n and a component that is perpendicular to n. The component that's perpendicular to n, that's like the part of the velocity vector that's flowing along the side of the surface. In other words, not coming through the surface. The part that is parallel to n, that's the part that's coming through the surface. So we only care about that part. So this is f evaluated at r of SKTJ dotted with this normal vector times the area of this patch, which is delta AKJ. Okay, so this then is equal to the sum k equals 1 to 5, j equals 1 to 5, f evaluated at SKTJ dotted with the normal vector at that point times delta AKJ. But notice that as the number of patches goes to infinity, this is exactly the surface integral of the function f dotted within ds. And how do we compute this? Well, this is the integral over the parameter domain in the ST plane of f of st, this is f of r of st, dotted within times the magnitude of rs cross rt dA, where dA is the dA in the ST plane. Now let's think about what the relationship is between n and rs cross rt. Well, rs cross rt is perpendicular to rs and rt. That is, it is perpendicular to the surface. Well, n is also perpendicular to the surface. So what this means is that n is equal to plus or minus rs cross rt divided by the magnitude of rs cross rt, because n is the outward unit normal vector. So normal means it's perpendicular to the surface. That means it's parallel to rs cross rt. Unit means that it has magnitude 1, so we have to divide rs cross rt by its magnitude, and outward means it is pointing outward. Rs cross rt could either point outward or inward. It's something that we have to check when we actually do these problems in practice. Okay, so what this means is that this is equal to the integral over d of the following. This is going to be f of r of st dotted with rs cross rt divided by the magnitude of rs cross rt times the magnitude of rs cross rt dA. This is actually plus or minus that. And this is equal to plus or minus the integral over d f of r of st dotted with rs cross rt d. Again, the reason we have the plus or minus is because we're going to be either asking for an outward pointing normal vector or an inward pointing normal vector, and we don't know whether rs cross rt is outward pointing or inward pointing. So if rs cross rt is pointing in the direction that we want it to point in, then the surface integral of the vector field is equal to this formula right here without the plus or minus. And if rs cross rt is pointing the opposite direction, then the surface integral of the vector field is going to be equal to minus the integral. Okay, the orientation is very important. The orientation of the vector, of the normal vector, is very important, and it's going to be part of the problem solving. Okay, so in other words, let me answer this part of the question. Let S be a surface with this parameterization. Let F be a vector field on R3. The integral of F over S is the following. It's the integral of the scalar field F dotted within ds, and as a practical matter, this is the integral over the parameter domain F dotted within, and we have to evaluate this. We have to evaluate this at the parameterization, so it's going to be F of R of st dotted with the normal vector, and then the ds, this is the surface area element. This is going to be times the magnitude of rs cross rt dA. And we will see this in action in the next video when we actually compute an example.